There's a more general topic of regression analysis, but we're going to focus on really the least squares line that we might use to not only fit a line, but to get us the conditional mean, and we'll also talk here about how we end up with the variance as well. Right? And before we head off into a numerical example, let's set the stage here between a response variable and a explanatory variable where we have collected joint data and now we're trying to decide how do we come along and put a line through this data. And this notion of the least squares for this regression or prediction line is all about the idea that if we come in and take a look at one specific point, that the error that we have between the predicted line and our actual one is right in here. Call that E sub I. And we're going to try to minimize the errors in the form of after we square them. Okay, so our basic model that we're going to employ is that y is equal to beta naught plus beta 1 times x plus some error. There's our intercept, and there of course is our slope. The predicted value will be beta naught plus beta 1 times xi, and then we'd have for a specific one the error for a specific one then is associated in that kind of manner. So this is the theoretical side over here, our model. Here's the implementation that we end up with, and because these are going to come from the sample data, these are also going to be estimates of what the true real beta naught beta 1 values ought to be. Now other textbooks, other authors are going to use A and B. They're going to use M for the slope, B for the intercept. There's a lot of variation out there between folks who do various writings about this. Right? Our residual is another name for this error, and we've got it over here. I'm just going to rewrite it that it's equal to our actual value minus our predicted value, and we can substitute in our expression up here. And also what we'll take a look at is the residual or error sum of squares. Now as we head off into this module, we're going to have an alphabet soup of terminology, and it can easily drive you nuts here. Your Montgomery and Runger text tends to focus on calling these errors. Other texts tend to call these residuals. I like the term residual from the standpoint of a statistical perspective, error from the standpoint of a probability theoretical perspective. So they're both equally good phrases. And one of the other things that you want to get used to is that with this alphabet soup that we tend to have somewhat sort of literal symbols and names for what we're doing. So this capital SS, which will absolutely be different than things that are the lowercase s, and the subscripts are going to become real important to us, but the capital SS stands for sum of squares. the subscript E for the error. So error sum of squares. And so we're going to sum up all of the squared error. And when we substitute in our expression for E sub I, then we get Y sub I minus beta naught minus beta 1. And I'm going to drop off the hats for a moment. Xi squared. Okay, I'll put them back in. Right? And just for convenience, I'm going to let that be equal to G beta naught beta 1. That some function, this one right here, all of that is a function of these two unknowns. Those are the ones that we don't know. That's what our goal is to find beta naught and beta 1 such that our error sum of squares is minimum, or we're going to minimize our function beta naught and beta 1. Right? And we do that with our classic use of integral calculus of multiple variables. So the partial of G with respect to beta naught will be set equal to 0, and this is actually not all, but just being a polynomial is not a hard one to do. Let's call that equation 1. We'll do the same thing for the other parameter, call that equation 2, and what you do then is you solve 1 and 2 for beta naught and beta 1. Right? And what you're going to end up with then is that our slope beta 1 is going to be equal to the sum of the mixed product terms xi times yi minus n times x bar times y bar, these being the sample means of the respective ones, divided by the sum of the x's squared minus n times x bar squared. And that can be rewritten as capital S sub xy over capital S xx. Right? And notice that these are really the same kinds of, if you think about this as like an operator, the same kinds of things. Sxy, capital Sxy, is the sum of the mixed product x and y minus n times the sample average of the first subscript times the sample average of the second subscript. Right? And likewise, when we come down to the denominator, known as capital S sub xx, we get the sum of the product of these two subscripts, so x squared simplified, minus n times then the sample mean of the first subscript times the sample mean of the second subscript. So that's the pattern that is sitting there. Right now, where you have to be real careful in your usage of these things are that we've got these double capital S's, right? And we also have such things as lowercase s with just one subscript. And it gets very confusing potentially, and you have to be quite careful as you're playing around with these guys, right? But this is just shorthand notation to make our development work and our communication and looking at computer output a little bit easier. The intercept value, beta naught, is going to be equal to y bar minus beta 1 times x bar. And note again, because the the beta 1s and beta naughts are really just functions of the data set, and since the random sample that we pulled is supposed to be just that, a subset of the overall one, that these all become then values with a little hat, meaning that they're sample values, not necessarily the true ones. They're point estimates of the true value. Okay. What we're going to do next is work with this and show you how to do the numbers, if you, not for the sole purpose of being able to grind out numbers and calculations, but rather so that you get a better sense of what happens when you are clicking buttons in software tools, selecting different kinds of options, and getting a feel for what the output is going to be, and how to then go back and interpret it and understand what that output is all about.